Hi everyone. I'm Daniel Parks. I'm part of IBM's product management team, working with Ceph. And today I wanted to share with you or discuss a little bit about stateful applications inside Kubernetes. So we see each day, a demand for having more critical applications running on Kubernetes, and these applications using state, so they need to persist their data. So there's also kind of a movement or requirement for having DR for those very critical applications. And we are going to go and have a look at just an overview of the different options that we have when we're working with Ceph regarding persistent volumes, and the different options that we have. But really today we're going to go deep into the details of synchronous replication, what we will call Metro DR. So this kind of solution where we have a very critical application that can tolerate any data loss, and we need to have synchronous replication for that data. We are going to have an overview of the different options that we have depending on the service level objectives that we have for our application, so depending on the RTO and the RPO that we have. And then I would also go into Ceph stretch mode, because for our synchronous replication offering, we are, let's say that the primary technology that we're using there is Ceph in a stretch mode. So we will go into a little bit of details about how we leverage Ceph in a stretch mode. And in the end, if we have 5 minutes, I will show you a small demo on how we fail over and fail back the application. So going into this slide, here I wanted to just cover the different options that we have inside Kubernetes depending on our service level objectives. So depending on the tolerance for data loss that we can have, and also the tolerance for our application downtime. So taking into account these two service level objectives, we have different options for our different applications and the needs of our applications. So the first one that we have here is backup and restore, the traditional kind of backup and restore of our data. As you can imagine, with backup and restore, the RPO, the tolerance for data loss is going to be big, because it depends, since we run the last backup that we had, we are going to lose all of that data up to the backup that we run. And also for the tolerance for up downtime is also going to be high, with backup and restore, because we actually need to put that data back into our cluster. We need to restore it. So we also need that time to restore the data. So with backup, we can have a good coverage for logical failures. We can also use it as a DR kind of solution, but we need an application that can have really high tolerance for RPO and RTO. With backups inside Kubernetes, we have the Velero API. That is a really nice API that we have, and we have also the OEDP community operator that makes use of the Velero API. It has a data mover. So it's a quite nice solution if we are looking for doing backups and restores inside Kubernetes. The next one that we have here is asynchronous replication, with regional DR, that we will cover a little bit afterwards, a little overview of what it does. But with regional DR being asynchronous, the tolerance for data loss, the RPO, is going to be in the range of minutes. It really depends on the interval that we set for our snapshots, for our mirroring between the volumes that we are using. So depending on that interval that we have set, the RPO could be bigger or lower. But it's going to be in the range of 5 minutes, 10 minutes, 15, depending on the interval that we set for our synchronous replication. And regarding RTO with asynchronous replication, here we are making use of the Open Cluster Manager that I will explain a little bit afterwards, but really what we have is like a higher level entity that is also not protecting our data, but it's also taking care of the failover and the failback of the application. So it's really full application protection. It's not only taking care of RPVs, but it's also taking care of moving our application between both of our sites in the case of a failure. So in that sense, the RTO is going to be very low, but it's going to be it depends on a couple of factors. The time that it takes for us to decide that that the site is down and that we have to apply the failover, And it also depends on the time for the application to start. No? We can have like this huge Java application that maybe takes 10 minutes to start, or a very fast application. No? So the RTO is going to depend primarily on those two factors, but it's going to be fairly quickly because all of the small details to actually start the application and fail it over between the sites is being taken care of for us. And finally, we have Metro DR. This is what we're going to go into details. With Metro DR, we can do synchronous replication. So in that sense, RPO is 0. No? So for our really critical applications, we have synchronous replication that is great. Again, the RTO is going to be in the range of minutes. It's going to be also taken care of for us by the Open Cluster Manager. No? That is going to make our life easier with the failover and the failback. So before we move into Metro DR and the synchronous replication, that we're going to go into detail in a moment, I just wanted to give you an overview of the synchronous replication. So here, what we have is 2 Kubernetes clusters. They are using Rook. They're deploying Ceph inside each of these regions. So in each region, we have a Kubernetes cluster with the help of Rook and its automation. We are deploying a Ceph cluster. So it's a Ceph containerized cluster running inside Kubernetes. We can see the monitors, the OSDs, all of them configured inside our clusters. And what we are doing is asynchronous volume replication between both of our sites. We are using RBD mirroring for our block volumes. So we are doing replication of those volumes on an interval that we set or we program. And for CephFS, for our read-write many volumes, they were currently using Bolsync to do that replication between both of the sites. Again, we have OCM, that is the multi-cluster or the Open Multi-Cluster Manager, and also with the help of Ramen DR, that I will cover in a moment, that is really an operator that is going to take care of all the small details to be able to fail over and fail back between both of the sites. The nice thing with asynchronous replication is that we don't have requirements for latency. So the latency is not going to be a stopper in this. We can have different regions. We can have the communication or the replication through a WAN. We don't need to have like dark fiber or very low latencies for this solution. Or we could also have like hybrid. We could be having one Kubernetes cluster on-premise and another one on the cloud and doing the replication between them. So in this case, latency is not an issue because we are going asynchronous. And then we have Metro DR. That is the one that we're going to cover a little bit, or synchronous replication that we're going to cover in detail. With Metro DR, with synchronous replication, the thing is that the main actor here is Ceph. So we have an external Ceph that we are using the Ceph stretch mode to stretch it between 2 data centers. We're going to call the data centers the one that actually have the OSDs and they're in the middle of the data path. And then we have an arbiter node that is really just a monitor, a tiebreaker, in case we have a network split between any of our sites. And here again, with the help of OCM, we're going to be able to fail over and fail back our applications. With Metro DR, the only thing, as you can imagine, this is synchronous, so we do have a strong prerequisite or requirement for latency. So we normally speak about 10 milliseconds between both of our data sites, because really if we go higher than that, just performance-wise, it's not going to make a lot of sense, because you're going to have so much latency by the time the client gets the acknowledgement back for that write, that maybe the solution doesn't make sense with higher latencies. Okay, so diving into the synchronous replication and going a little bit more into details about this solution. As you can see in this slide, is like the projects that are involved to give us the full picture and being able to have real full application, DR protection for our applications. So here we have different upstream projects. The first one is the multi-cluster manager layer, where we have open cluster management. The open cluster management, as I said, it's like we'll normally have it on a third site, and it's really taking care of failing over and failing back our applications between the managed clusters. So it's a higher level entity He's aware if we have a failure on a site, and then an operator can decide to fail over or fail back the application depending on the use case. The Open Cluster Manager is helped by Ramen. No, the Ramen DR is an operator that really has all of the intelligence, all of the automation to be able to actually fail over and fail back the application, take care of all of these little details, no, that otherwise we will have to do manually. And then we have the platform. So for the platform, it's just any Kubernetes cluster that we can deploy. It's true that because we are using operators, it's a good idea to also have the operator lifecycle manager available on your Kubernetes cluster, so you can deploy operators and make use of the advantages, no, that they give us, like, for example, Ramen DR. And then finally, the persistent layer. So as we spoke about, no, here is where Ceph comes into play. We are going to use Ceph in a stretch mode between our sites, and also we have the help of Rook. Rook is going to, as we said, no, is going to help us with all of the automation. In this case, we are using external Rook, and I will go that into details in this slide. That is actually helping us connect to our external Ceph cluster. And that's why I had this slide here that is just very quickly to mention how we can leverage Rook to deploy Ceph in our Kubernetes clusters. So you have, let's say, two modes where you can go internal mode. In internal mode, you're deploying with Rook Ceph inside your Kubernetes cluster. So you're going to see there all of your monitors, your OSDs, everything running inside the worker nodes for Kubernetes. And then we have external mode. That external mode is really just connecting to our storage, our Ceph storage layer with the help of Rook. And in Rook, in this case, what is really helping us that is very useful is to configure all of our CSI drivers. So it's going to manage all of the connections, the provisioner, and also the drivers for the CSI to be able to consume the Ceph cluster storage in a simple way. Okay, I'm not sure if you can see this too well now with it. I was expecting for a little bit bigger screen, but anyway, I can walk you through it. What I wanted to show you really here is just some diagrams, and I want to show you a normal Ceph deployment, and then we can go into details or compare it to a stretch, Ceph stretch cluster deployment, and we can talk a little bit about the details, no, the differences. Here's just a normal Ceph cluster, 6 nodes, we have our monitors, our managers deployed, everything is in one site, and then this is really offering block, no, for read-write once. We have shared file system with CephFS for read-write many for our Kubernetes clusters, and we also have available the S3 RGW endpoints to consume. And then what we can do with this configuration is connect one Kubernetes cluster, again, with the help of Rook in external mode, or we could actually connect n clusters, no, how many clusters we will need for our configuration. How we connect these Kubernetes clusters, we can really leverage multi-tenancy in the sense that we can have a specific pools for each of our OpenShift clusters, or maybe we just want to have different namespaces, so we can just share the same pools for all of our clusters, no, depending a little bit on the use case that we have. Okay, so this will be like a kind of a single, well, not single, but just a single site deployment, no, a normal Ceph deployment, and now we are moving into Ceph in a stretch mode. So in a stretch mode, now that we have in this diagram, in this slide, the first thing that you can see is that we have 3 sites. So we have data site 1 and data site 2, and then we have an arbiter site. No? So the first thing that you can see is that we have a requirement for 3 sites. All of the boxes here that you see is the same cluster. Now, even if you see different boxes, what I'm showing in this diagram, all of it is the same Ceph cluster that we are using. The only thing that is stretched between 3 sites. One small detail, you can see that the subnets that we are using are different between the 3 sites. So we are really using level 3 and routing between the sites. That's perfectly normal, and Ceph works great like that. Other thing that you can see here is that the requirement between our data sites, where we have the OSDs, is what we call the data sites. We have this requirement or recommendation for 10 milliseconds round trip time now between the sites for the, as we said before, for the performance to make sense. But the nice thing with Ceph in a stretch mode is that we can also have an arbiter site, as we call it, that doesn't have any OSDs. So it's really not on the data path. And in the sense that the really nice thing of not being in the data path is that we can have higher latencies. No? So you can see here that we have tested more or less with 100 milliseconds. It can be in that ballpark, no? More or less to have that latency is going to work fine, and it's not going to affect our performance in any way, because really it's not in the middle of the data path of the OSDs. The Arbiter side, as you can imagine, it has a monitor. So you can see in the diagrams that we have 2 monitors on each side, and then we have the 5th monitor on the Arbiter side. This is going to be really important, no, the role it plays, because if we lose a full site, we still have 3 monitors to provide us high availability. Other details from here. Well, as you can see, on both of the data sites, we have 1 RGW in each. We have 1 manager on each, 1 MDS on each cluster. This is really a simplified deployment. No, it's really small, only 7 nodes. But you can imagine that what we are trying to achieve here is that we don't have a single point of failure in case we lose a full site. No? So we are prepared to always have 1 service on each site at a minimum. No? So continuing with the same example that we had before, we offer a shared storage layer with block and file system to our Kubernetes clusters that we are going to connect now to this stretch cluster. One thing that I wanted to mention, no, that is very important, is that we need to have replica 4. No? So currently, when we are working with Ceph in a stretch mode, replica 4 is needed. No, the erasure coding, for example, is not supported. So we need to take into account that in the end it is an expensive solution. No, we have 4 copies of all of the data, but that's what we have to work with if we really want to protect our critical data in a synchronous way. The idea that why we have replica 4 is because we are going to configure a crash map. So each time that we make a write, we are sure that we are storing 2 copies on site 1 and then 2 copies on site 2. No? So we can tolerate a full failure of a site, and we still have 2 replicas available on the other side for that object. So going on, moving forward, here we have added our Kubernetes clusters. These are, again, using Rook external to connect to our stretch cluster. And you can see that now we have 1 more cluster here that is OCM. This is our hub cluster. Is this higher level entity that we were speaking about before. That is the one that is going to actually deploy the application for us, and then it's going to be able to fail over and fail back the application. No, he's really taking part. And both of these clusters are a managed cluster of the hub. No? Okay, so I wanted to walk you through what a failover of an application looks like with a diagram. This is exactly the same diagram as we had before. I'm just adding the global load balancer at the top, but it's just the same. And here we deploy an application. In this case, we are deploying the application through OCM, through the Open Cluster Manager. It has several different ways of deploying. So maybe you could use a subscription. You could use an application set for Argo CD, for example. No? So you have different ways of deploying that application in a kind of a GitOps manner, no? In a declarative way. In this case, we could use any of them. The thing is that we are using a GitHub repo with all of the YAMLs that define the state of our application or the configuration for our app. And that app gets deployed on site 1, and it's consuming a persistent volume from our Ceph stretch cluster. Let's say that we have an issue. Our Kubernetes cluster burns down. We have a problem, a disaster, and then let's say that the global load balancer detects that there is an issue. The health check fails for that global load balancer, so the client requests are not going to go through there anymore. And we, or as an admin or an operator, you have to take the decision to fail over. So what is currently not in place is automatically detecting a failure and moving over the load, because that's like a kind of a dangerous operation, and this is something that has to be decided by the administrator, by the operator, maybe the owner of the application, to actually initiate the failover, and so it actually starts moving to the other side. So once we initiate the failover, now we have taken the decision to failover. One really important thing that we have to do is actually fence the cluster. So we have to cut the communications from all of the worker nodes that we are failing, the site that is failing. We have to cut those communications, so we are very sure that we are not going to mount the same volume on both of the sites at the same time, no? Because that for sure could bring corruption to the file system that is being mounted. So we are using the OSD block list provided by Ceph to actually do I/O fencing, no? and blocking the access to the data from site 1. Once we have done the fencing, we can start failover the application to the other site. That failover is going to be taken care, as we said before, by RAMNDR and also the OCM hub. So the OCM hub is going to take care, using again the GitHub repo, to start the application on site 2. And RAMNDR is going to take care of recreating or redeploying the PV and PVC definition, no? So we are going to be able to access the same exact volume that we were accessing on site 1. That, because we're doing stretch, we have synchronous, so we are not going to have any data loss. We are also able to access that same volume from site 2, and then we will be able to start our application and start serving client data again, no? This is just the fallback, no, the failback. It will be, again, once our cluster is recovered inside 1, we remove the network fence that we have set, and we are able to do the failback, no, as we call it, relocate to the primary site and start or keep working like you were before, no, in a normal way. We are able to achieve this, as we said, no, with an RPO of 0, with no data loss, because this is really synchronous replication thanks to our Ceph external cluster that we have, no? And I wanted to just very quickly explain you a little bit what happens inside Ceph when we lose the actual data side, no? Because we just wanted to have a couple of details about if we lose Ceph, the higher level, let's say that we're not losing a full site. If we lose Ceph, the higher level is really not going to almost notice that we have lost Ceph, because we are working in this stretch mode, and this is what I wanted to show you. So let's imagine that we have a failure on a Ceph cluster. We have lost our site, data site 1, the nodes in data site 1. One of the first things that is going to happen is that thanks to the tiebreaker, we are going to be able to keep quorum on our monitors, so we are in a good spot. We have 3 monitors thanks to the Arbiter site, and we are going to be able to keep quorum, so the clients are going to be able to do reads and writes without any problems. The other thing that happens is we need to detect that these OSDs are down inside 1, so it's going to take the amount of time that it normally gets to declare the OSD down. During that time, as you know, those 20 seconds, maybe for the OSDs that are primary, you could see a little hiccup, no, in the I/O for the clients that are right into the primary until it's detected, no, and move that primary to the OSD to the other side. But it's just a small hiccup that the application is going to see. And regarding Ceph, what is going to happen is that all of the OSDs are declared down. So all of the nodes are also declared down. And at that moment, Ceph knows that the full data center is down. When this happens, it goes into what is called like degraded stretch mode, meaning that it's going to do a certain actions for us. So I mentioned before that when we use this solution, we have replica 4, no? So we are saving 2 copies here and 2 copies here. One of the things that is going to happen when it goes into degraded stretch mode is the min size is changed, no? From 2 to 1. We do that change because you know that with min size is the minimum available copies that we can have we need to do reads and writes. So because we are going to remain with only one site, we want to have replica 2 and min size 1, no? So that's going to happen automatically for us, no? Without any manual intervention. As soon as Ceph detects that it's in degraded mode, it will do these changes for us in all of the pools. Also, because we're using, during an amount of period of time, replica 2, it's also recommended to only use this solution when we are working with flash media, not just because it has higher endurance and also is able to recover faster. No, if we have another failure, it's able to do the recovery and the rebalancing faster. The other thing that we have here is that there's a special stretch mode flag that is set, so even if our size is going to keep the value of 4, when we remain with a single site, it's not going to look for new OSDs to try to fulfill the amount of 4 copies. It's going to stay only with 2 without trying to go to 4. No? But all of this is really done for us by the cluster. I'm just trying to go a little bit now into the details just to see what's happening underneath. And once we get to this point where we have the Ceph nodes that are recovered, what is going to happen is that the cluster enters what is called like recovery stretch mode, and then peering is allowed again between both of the sites, and then it's just a normal process. No, the peering happens, the OSDs agree on the changes that it needs to copy from the remaining site to the one that is coming up that has missed certain changes now, so the changes are recovered, and everything goes, all of the OSDs now in the fail site go back to up, and you are on a normal state again, and you are ready to continue working without interruption or almost just a small hiccup to the client I/O. So that's a little bit what happens to Ceph on the underlying level. And I wanted to show you very quickly, without going into a lot of details because we don't have time, just a very, very quick demo of what is going on here, so how it works. The only thing, I'm not sure if I can show you, if you're able to see it very well, but just to give you a little bit of context of what we have. We have, in this case, we have 2 OpenShift clusters. This interface that you see here is Open Cluster Manager that is running on a Kubernetes cluster. I'm using OpenShift just because I'm using single node OpenShift, but it could be any Kubernetes cluster that has OLM. And I have a cluster 1 here that is going to be my primary data site where I have my application running. I have cluster 2. This is my secondary site where I want to fail over my application. And finally, I have my hub cluster. Now, this is where we have OCM, that higher level that we spoke about, that is able to fail over and fail back the applications between the sites. Regarding Ceph, let me make this a little bit bigger. So with Ceph, just a very basic deployment that I have here. We do a Ceph OSD tree. You can see that we have 2 data centers. Each data center has 3 hosts, and each host has 2 OSDs. So really what I have configured is a crash map that is going to make sure that I store out of my size 4 replica that I am using. It's going to make sure that I deploy or that I save 2 objects to data center 1 and 2 objects to data center 2, so I can tolerate the failure of one of my sites. And this is not the best output. It's really ugly, but I just wanted to show you here how you see size 4 and min size 2. This is going to, once we enable a stretch mode and we set it with a Ceph command, Ceph automatically is going to go through all of our pools and it's going to set size 4 and min size 2 for all of us. That automatically happens when you enable a stretch mode. And the other thing, the last one that I wanted to show you from this is if we do a Ceph mon dump, just to get the info from the monitors. Here you can see that we're using election strategy number 3. This is the election strategy that we use for in a stretch mode that is really, it has more intelligence than the classic mode. It's really doing pings and it has scores for the different monitors. So it's able to keep like a history of the responsiveness of all of the monitors and then it has a score. No? So it's really advanced to try and avoid network splits. No? When you have a split with the network is coming and going. This is going to help with those kind of situations. And from also there, you can see that I have a stretch mode. It is enabled, and our tiebreaker, our monitor is Ceph 6. And then we also are using some tags to define the crash location. No? So we have data center 1, data center 2 with 2 monitors each, and finally our tiebreaker that is Ceph 6. Nope, here. Okay, and to the application that I wanted to show you, I'm just going to run this here. What I wanted to show you is just a Rocket Chat application that I have deployed. So if we go here, this is just Rocket Chat. It's a messenger, kind of a messenger where we publish our messages. And what I'm doing is that using this script, I'm just running a message there. I'm sending every 10 seconds, I'm sending a new message to the chat. And this is just a very basic example, but it's going to help us to determine that we are not losing any messages, so that our RPO is actually 0. I'm also comparing the time that it takes to fail over to the second site. We can have more or less an idea of the RTO. No? So this is my site 1, and in this this is my second site, my second Kubernetes cluster that currently is down. No? So what I'm going to do is actually fail over to this cluster. I have a script here just to make our life easier. We can use this one to fence the site from one side to the other. And really what it's actually doing is using a couple of CRs that are made available for us by Ramen, but that operator that I mentioned before. So these CRs, really what we're going to do is use one to fence the cluster, as we mentioned. And once the cluster has been fenced, what we are going to do is actually use the action to fail over our application to the second site. While that is happening, we have a view inside the Open Cluster Manager. There is a view to actually check the applications, and we can maybe go here and take a look at the topology. This is really small. Let's make it bigger. Here, I just wanted to show you a couple of things. This application, this Rocket Chat application, is using MongoDB. So we have a persistent volume that we are consuming from our external Ceph cluster using the storage class of Ceph RBD that we have here. So really it's a persistent volume, read write once volume that we are using now for our MongoDB database. And the other thing that you can see here is that we have the cluster and that it has already failed over to cluster 2. No? So it has been able to do the failover right now from cluster 1. It's right now running on cluster 2. And now we just have to wait for the time it takes for the application to start, no? Because it's using MongoDB and the front-end application. So it may take a little while until it starts running. And we have everything there in green. No? That it seems that everything is in green now here also with the deployment config. So if now we go back to our site 1, this is where it was running before. You can see that now we have lost the connection. Our last message is message 4. And now we're going to try and refresh on the second site and see if the application is actually up and running in this site. It may take a little while because it's also going very slowly, but it should, in the end, we should get here the Rocket Chat up and running. The thing is, let me just, so we can see it better without any messages, just stop the script so we don't get any output. Also, maybe I can make this a little bit bigger so you can see it better. Okay, so what has happened here is that we are now in site 2. We can see that the last message that we have from site 1 is message 4. So we haven't lost any messages between the failover and the failback. And we can see also that the RTO, so the time it takes to stop the application on one site and do the failover, has been around 2 minutes, no more or less, to do that operation. And that's a little bit what I wanted to show you with this small demo, no? So that's all I had for you today. I have some links in the slides if you want to take a look afterwards regarding documentation and where you can test this, because all of this can be done with the upstream bits. It works really great, so you can check out all of the projects that are there and also test it by yourselves. No? So that's all I had, so thanks a lot for your time. And if you have any questions, we still have a little bit of time. Yeah, go ahead. I think maybe the mic works, so you can give it a go.
Did you consider looking at a three data site replication? Would that kind of remove the need for arbitrary? You can use basically 3 replicas then?
Yep. Yeah, the nice thing, that's perfectly fine. You could also have, as you said, no, instead of stretching between 2 sites, a stretch between 3 sites, but also have OSDs on that third site, and that would work fine. No? The nice thing that we did with this idea is that we find a lot of customers that only have access to 2 sites with really low latencies, and then you have maybe, even with 100 milliseconds, you could use a cloud provider with a VM for that arbiter, no? So it's really giving you that flexibility for that kind of use case. But to answer your question, yes, you could perfectly also do a stretch, no, with 3 sites and 3 OSDs on the 3 sites, no, for example.
Sorry, do you have a question?
Yeah, small question. So the prerequisite for using this Metro DR is like we have to need an external cluster. We cannot do for the normal cluster, right?
What, sorry, you need?
External cluster.
Yes. At the moment, the external cluster is a need, yeah. Because as you can see, we're really stretching that external cluster. There is another option using ODF internal and stretching that Rook is able to help you with that, no? Where you can stretch and use something similar. But the only difference is that in that kind of configuration, you're stretching OpenShift and you're stretching ODF or Ceph or Rook or whatever you're using, no, for that. In this case, the nice thing that we have is that we are not stretching the OpenShift cluster. So the requirements for the latency for the master nodes, you know that etcd, is very picky with the latency. This is not an issue in this situation, no, because we have separated OpenShift clusters on different sites.
Yeah, and one more I am confused in. So for regional DR, you said it's asynchronous and this is synchronous. So maybe can you throw some lights why it is like that?
Yeah, so this one is for sure synchronous now in the sense that we are using OSDs and we are putting copies on each of the sites with this external mode, no? And the difference with the asynchronous one, with the previous example that I had for asynchronous, is that really you have 2 different Ceph clusters, so there's 2 completely different Ceph clusters, and we are replicating each of the volumes for each of the clusters between them. So we're doing asynchronous replication. Really what's happening is that you take a snapshot of that volume, and then that snapshot is replicated to the other side, no? So that's why it's asynchronous, and there's really no requirement for latency or no requirement for having a stretch mode, because in that case, you just need 2 different OpenShift clusters with 2 different root deployments, Ceph deployments, and then you do asynchronous between the sites.
Maybe this can be also done in an asynchronous way. But yeah, like if maybe both can done at synchronous and both can be asynchronous at the same time.
Yeah, you could do something like with this, and then it's not very easy to do, but you could have like a synchronous and then send to another cluster in a synchronous way, no? You could have a combination of both, no?
Yep, thanks.
Thank you. So very interesting. Thanks a lot for the talk. I have a question which is actually very similar to this one. So to me, it looks like the storage is actually active-active because you have this stretch mode and basically writes are synchronous and you make sure that you have always enough copies to keep Ceph alive. The PGs are able to I/O so that you can access your data. But I was surprised by the fact that the application itself and the 2 Kubernetes clusters, OpenShift in this case, they are actually coupled and the failover of the application, it's a sort of a manual failover. You said that someone has to take the decision to push the button and say, okay, the cluster is gone. I'm failing over my workloads to the new one. So I understand the latency requirements on etcd. Do you think that the failover of the application can be somehow automated? Because like in this case, you were using RBDs, which is a bit tricky because unless the application knows what it has to do, you don't want to multi-attach because eventually you will corrupt the file system. But if you're using CephFS, you could actually have different pods mounting the same CephFS subvolume, and you can actually have multiple pods, multiple containers being behind the very same load balancer, and that would really be active-active. So
a couple of details, and that's a very good point, no? But you had like 2 or 3 different points there that are very good. But let's say that if you're using CephFS, if you're using read-write many, as you said, nobody, because this is a stretch layer, nobody is stopping you having active and in the application even, no? So you could have the same application with CephFS, both of the volumes mounted and consuming the data. That's something that you could do, but at the moment it's outside of what the RAM and DR operator can do for you, but you could perfectly go and manually mount it and it's going to work for you, no? Okay. But that automation is not there. It's something that maybe is going to be looked at a little bit further down the line. But that would be a perfect example of being able to have active, no, with CephFS. And the other point that you were making with being active passive, in this case, we can have, let's say, in both sides, we can have certain applications active here and certain applications active on the other one, and then they can cross failover, no? But it has to be active passive in this moment, especially as you mentioned with RBD, you have read-write once. That's why we're doing a network fencing, no, to be sure that we don't mount it on both sides at the same time. Yeah, sorry, go ahead. You were going to also ask a question.
What are the future plans to kind of work on? One, you said that CephFS-based mirroring in the background, or maybe mounting for CephFS. In general, like, are there any scope of improvements, or how do you see in future this feature to be scaled out, maybe?
So you mean for the use case that we're seeing here for the stretch cluster, RPO0, and being able to have like kind of active applications?
Yeah, kind of like one point he brought as well, kind of bringing the automation of failover mechanism in some way, being more intelligent.
Yeah, the only thing that there is a decision that, let's say that that more or less has been taken in that project, just because it can be dangerous in the sense that you have to know when to take that right decision. But for example, nobody is stopping you from doing some configuration by yourself and checking the health check of the application, for example. Mm-hmm. And if you write some stuff where you check the health check of the application and you decide that health check is not working, you could push the failover automatically, no, with automation. Nobody is stopping doing that, no, if you want to take that decision. But inside the actual product right now, as it is kind of a manual decision, and it's something that is thought through to be manual, just to be sure that you want to fail over the application. No, it's not happening by a mistake or kind of a failure.
Also, how can we work this out in open source version? Maybe like is Metro DR RAM in open source as well as
everything? Yeah, and the demo that I did is everything just by OpenShift. That is the only thing, because running Kubernetes single node is a little bit of a pain. So I used OpenShift, but I used all upstream bits in what you saw in the demo. So everything is there. And in this slide, you can see all of the projects, all of them upstream, and it works fine. And I have used them for this demo, so yeah, for sure you can try it out. Everything upstream, no?
Yeah, maybe upstream solution deployment, if you can work out, that would also be interesting to see. Yeah, I think I forgot the next question. But yeah, maybe how's the external cluster being orchestrating this thing? Is it interacting with RAM and DR, or is it just for the management of Ceph?
Yeah, no, that's a very good point, because RAM and DR also has a volume group VRGs now, so it has also little bits or operators inside the managed clusters. So it's also taking care, for example, if we are using asynchronous on the replication that we're doing from one side to the other, or in this case, it's taking care of the PVs and the PVCs for us. So yeah, for sure you have little bits also of ramming, taking care of that replication between the sides, or if it's synchronous in this case, of actually removing the PVCs from one and then moving them to the other. So on your managed clusters, you're also going to have some RAM and DR bits there that are going to help you do the network fencing and all the things that take care of failing over.
So failover is completely RAM and DR thing, and external cluster is mostly for Ceph and PVC provisioning.
Yes, really.
Okay.
Ceph is there to provide the storage layer, but then it's ramming with the help of Rook, the one that is taking two decisions on how to actually fail over. But the Ceph is just a storage layer.
Okay.
And for example, Ramen is leveraging the block list, the OSD block list, to actually do network fencing, that kind of stuff. But the intelligence is in Ramen, not automation is in Ramen.
Yeah. Anybody else?
What are the consequences if the arbiter node goes down?
If you lose the arbiter node, you mean? So if you only lose the arbiter node, everything is going to keep working fine because you have 4 monitors. If you lose the arbiter node on one side, you have an issue, and there is a problem there because you don't have quorum on the monitor. You only have 2 monitors outside of 5. So then all of your client IO is going to be interrupted.
Are there any performance-based testing done on this as well?
Yeah, that's a good point. We have some initial testing, and there are several things to take into account here. One is replica 4, and replica 4, as you can imagine, is painful. So you're going to have a performance hit. It's something that you have to assume because you have a critical application, and you're doing 1 copy more than you would normally do. And then you have to add the factor that you are also going through sites. So we are storing 2 copies on one and 2 copies on another. So each write is going to the other side, and you have the penalty of the latency, the round trip time between both of your sites. So there are some drawbacks with this kind of thing, but it's also providing you with an RPO0 of critical data. No?
Okay.
I think that the initial testing, there's also a lot of work going on with read affinity. So at least you can read and have read affinity of the OSDs that are on your same site to try and make things a little bit nicer. But there is a penalty, no, going to the site.
Consistency demands penalty. Anybody? No? Thank you. It was great.
Yeah, thank you. Thank you for your time.